This problem and all other data structure problems can be found here at Sarai Studies. Link is in the description box below. Below is an array representing a binary heap for a min heap. Show the array contents after inserting one. So we are going to just do this as a tree first. So I see the last key, I go up, I see its index, 12. That means I need 12 nodes. So I start with what a binary tree is, which is just every node having 2 children. So I keep adding 2 children until I get to 12. Right now I'm at 7. From left to right, 8, 9, 10, 11, and then 12. And then I also like to specify my node lengths. Then I split the tree into rows or levels, and I use that to help me number my nodes. So I just go by row from left to right. So 1, and then 2 and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then the same thing over here with these numbers. I'm just going to write them in order, starting from row 1, and then when I run out of nodes, I go to the next row, so starting from left to right. I'm going to write it. So 2, 3, 9, 7, 5, 12, 20, 7, 11, 20, 14, 18. So this is just the tree that was given to us, but we have to show it when 1 is inserted. We know this is a min heap because we see that every parent is smaller or equal to both of its children. So here this is 3, smaller than 7 and 5. Here this is 9, it's smaller than 12 and 20. So that's what a min heap means. Min for small, parent is smaller than both of its children or equal to. When we want to insert a key, we always do it from the next available spot in the row, which is this one right here. I want to insert 1, so I'm just going to put in a 1 there. Beautiful. So that's the first step. But then the issue is, this is a min heap. After every operation you do, you always have to make sure that the property of your tree is satisfied. What's the property of a min heap? That all parents have to be smaller than or equal to both of its children. If we take a look at the tree of the node that we just added, this parent is not smaller than 1. So that's a problem. So what we have to do is we have to have 1 swim up until this property is satisfied. So how do we get this one to go up? Well, the only path is through this one over here. So we have to swap 12 and 1. Then we check again. Over here, is this parent smaller than or equal to both of its children? Yes, 1 is smaller than 18 and 12. But we also have to check the other subtree connected to the one we're working with, which is this tree right here. Is this parent smaller than or equal to both of its children? It's actually bigger than 1, and that's not good in a min heap. So we want to go ahead and have 1 swim up again. So we swap again, and then we check. This tree, is the parent smaller than or equal to both of its children? Yes, 1 is smaller than 9 and 20. But we also have to check the other tree connected to the one we're working with. Is this parent smaller than or equal to both of its children? No. 2 is actually bigger than 1. That's a problem in a min heap. We want the parent to always be smaller. So what can we do? Well, we can have 1 swim up again. And the only way it can go from here to here is by following this path and swapping with 2. And then again, we check, is this parent smaller than or equal to both of its children? Yes, 1 is smaller than 3 and 2, and therefore we can stop. So we swim by swapping with the node above it. But they want the array contents after inserting 1, so we have to translate this into an array. Remember, we never start at 0, we start at 1. We already know what everything is. At 1, it's 1. At index 2, it's 3. At index 3, it's 2. Or you can just notice that you're going in order of the rows from left to right. So then comes 7, 5, 9, 20, which are all in one row, and then 7, 11, 20, 14, 18, and 12. And notice we started with 12 nodes. Now we end up with 13 nodes. Why? Because we inserted a node. So that makes sense. I'll see you in the next video. Have a good day.